Welcome to another edition of Math for No Reason. In this edition, we will be proving this well-known result. The result states that if we have a polynomial equation with real coefficients, then its complex roots would occur in conjugate pairs. More specifically, if z is a root of this polynomial equation, fx is equal to a0 plus a1x plus a2x square up to an x power n equal to 0, where all of these coefficients a0, a1 up to an are real numbers, then z conjugate is also a root of fx is equal to 0. Now, to prove this result, we will be using an important property that can be easily proved using the Euler formula. It states that if you are looking at z power n and you take the conjugate of that, so if you are looking at z power n conjugate where z is a complex number, then this is equal to z conjugate power n. Now, this is easy to see. So, if z is equal to r e to the power I theta, then z conjugate is r e to the power minus I theta. Z power n is r to the power n e to the power I n theta. Z to the power n conjugate is r power n e to the power minus I n theta. Now we see that r power n e to the power minus I n theta is equal to r e to the power minus I theta to the power n, which is exactly this result. Now, we will use this and the fact that if you have two complex numbers u and v and you take the conjugate of that, then the conjugate breaks up, so it becomes u conjugate plus v conjugate. So, these will be the two main results that we will be using for proving this theorem. So, let us do that. So, let fx, which is a0 plus a1x plus a2x square plus anx power n, be represented as alpha x plus I beta x. Now, alpha x and beta x are real numbers depending on x. In particular, when we are dealing with z, so if you are looking at fz, then we will have alpha z plus I beta z, where alpha z and beta z are two real numbers, and we will write this as a plus ib. Now, since fz is equal to 0, we have a equal to b equal to 0. This is an important thing to remember, that in this representation, if fz is equal to 0, then a equal to b equal to 0. Now, if we look at fz conjugate using the property that we just mentioned, we will have, again, if we are looking at fz conjugate, then this is a0 plus a1z plus a2z square up to an z power n conjugate of that, and this turns out, since a0 a1 are all real numbers, and using the fact that we mentioned that z power n conjugate is z conjugate to the power n, we will use that to write this as, and note that this is nothing but f of. So, we have showed that f of z conjugate is equal to f conjugate, f z conjugate. So, since fz is a plus ib, where a and b are two real numbers and we are looking at the conjugate of that, so this becomes a minus ib. But we have seen that a and b are 0 because fz is equal to 0. So, we have seen that earlier, that fz is equal to 0 implies that a equal to b is equal to 0. and therefore f z conjugate is also equal to 0. So therefore z conjugate is also a root of fx is equal to 6. That's a good point to stop. Thank you.